So first of all, a few updates. Sorry, there's a typo here. What I meant is that assignment 2, okay? Assignment 2 is going to be released by the end of today. Actually, I already have everything ready, but this assignment will include some materials. I guess most of the materials we covered today, so I really wanted to wait until this class is finished to see how much we can do for the assignment questions I already prepared, right? So depend on the progress of today's class. Originally, as you know, the due date was a week later, next Monday, but since I didn't get to post it by this morning, so I was thinking that maybe it's a good idea for me to give you one more day. So I'll post it today, and then you will need to submit your work by the end of next Tuesday. So that will give you at least a little bit more than 1 week, okay? So that's about assignment 2. So before the assignment 2 will be due, we will have another Q&A session hosted by the TA in Microsoft Teams. It's of course optional, but in case you do want to seek some clarification or assistance on the assignment or on any other topics of the course, please feel free to join the Microsoft Teams meeting. You can go to Avenue to Learn. The links are all posted there, or you can directly launch your Microsoft Teams, go to the channel for this course. You will see a meeting going on during the scheduled time. Okay, so it's going to be Wednesday, that's 2 days from now. Lastly, we have the final exam finally scheduled by the MBA program office. I think the last class of this course is December 2nd, right? So it's going to be 1 week later. And things are pretty much similar in terms of how they're supposed to work. But there's one small difference. We start at 11:30 instead of 11:45 because that's the preference by the MBA office. They told me that they prefer to have the same schedule as the class time for consistency with other courses so that people don't get confused. But as last time, I would suggest that maybe you can show up a few minutes earlier, maybe 5-10 minutes earlier, so that you can get ready for your computer, for everything else. Okay. So those are the updates I wanted to mention. Also, a quick word about the midterm test we had last week. So the TA is still actually trying to finalizing the last few touches on grading. I expect that things will become ready pretty soon in the next couple of days. How do you feel about the exams? Well, based on what I heard, it seemed to be a bit intensive, right? So it's maybe many of you didn't get to finish everything. But the good thing is that I took a look at the grading. It's not completely finished, but I think things are looking okay. I mean, on the average, people are doing quite well. But the important thing is really to learn instead of creating a difficult exam or easy exam in the course as something you have to go through, right? So what I intend to do is that after the grading is done, I'm gonna post the solution to the exam. You can take a look, and I think on the average we are doing quite well, but there's some common issues like how to make things more efficient, so that for tests like this you can have more time by the end of the test, right? So you can take a look, and the important thing is again to learn from what we have worked on, right? So so then that's pretty much the important things I wanted to say before starting today's class. Okay, so do we have anything you want to address before we move to today's contents? Yes, please.
Is a group project?
Oh yeah, group project is gonna be due last day of class. So basically, our last day of class for this, for this course is December 2nd, but I was referring to the last day of class for all courses. I think it's the Thursday of the final week before the exam period. Okay? Because there's a policy saying that we cannot set a deadline later than the last day of class, given that we do have a final exam. Of course, with the final exam, anything else, any other components must be finalized, not finalized, the due before the last day of classes. Okay. Okay. Thank you for the question. Anything else?
I felt like 2 hours was kind of like not enough for doing the exam.
Yeah, I mean maybe, but it's the same thing. I mean, it's common for everybody. So what's more important is the relative performance instead of the absolute performance.
Because I was getting like errors in between and then
Yeah. I mean,
resolve them.
well, the final exam is actually already scheduled. It's going to be still 2 hours, but I can maybe adjust the number of questions. So I will try to make it, better in terms of the amount of work in the final exam relative to the time allowance of 2 hours in the final exam. But I think again, more important thing is that we worked on it and make some effort, right, and learn something, and the result. I mean, regardless of the distribution of marks, I think that I expect that the average grade of the course will be somehow quite reasonable. Yeah. Okay. So anyways, the results of the midterm, the grades of the midterm will be posted in the next few days, and you can always feel free to reach out to me to discuss about the test and the grading of the test. All right, so anything else? Okay, so now let's dive into today's topic. So today we are continuing to talk about classification. Very quick review about this type of problems. So basically, this is something within the category of supervised learning where we typically want to make some predictions, right? So we are given some features of the records in the data, and then we want to predict the outcomes. For classification problems, the outcomes are generally class labels, right? We're going to be seeing the specific example we will work on today. But for most of the classification part in our course, we're going to focus on the simpler case, which is binary classification, right? The outcome is either 0 or 1, positive or negative, right? And then the main method we're going to use for today is logistic regression. Now remember, logistic regression is somehow very similar to linear regression, but it tries to predict something kind of specific, right? Because we have, let's say we have a binary classification problems. Is the application going to be approved or not approved? Is it going to be 1 or 0? And then before we know anything, we need to think about the probability of the outcome being 1 or being 0, right? So logistic regression focuses on predicting the probability of a certain record belonging to the positive class or negative class, okay? And then in order to predict the probability, it's typically not a good idea to use a linear function because linear function is not guaranteed to have outcome that is between 0 and 1, and that is a requirement for you to estimate the probability, right? Instead, we'll first calculate a linear function based on the features. And we have the features typically represented by x's, and then we will have model parameters, like b0 here in this formula is going to be the intercept, and we have a coefficient for every single feature. Based on this linear quantity we calculate, we further apply a function that we call the decision function or the sigmoid function. And then that will help us convert the linear result into a term that is between 0 and 1. And the math here is not super important, but that is the main idea, right? And that's why people typically say that even though logistic regression is not a linear regression, but it's one of the models which we always refer to generalized linear models, because we first deal with the linear function and then convert that function to a quantity between 0 and 1. And we use that as the probability of a certain object or a certain record to have the class label being 1. Right? Remember, typically 1 means positive. And depending on the context, it can define what is positive, what is negative. But the main idea is that we want to predict the probability of a certain record with given features of belonging to the class that is labeled as 1. Okay. Anyways, that's just a quick review, and now we're going to go back and look at the Jupyter notebooks to work on a particular example. All right, so let's look at a classification problem, and particularly the problem is about predicting no-shows. So let me explain what is the problem of predicting no-shows. We know that when we need to see our family doctor or visit some medical specialist or even for other kind of situations, it's very common that we have to first call them or book online for an appointment, right? So typically you get an appointment maybe in a few days, or sometimes if the wait list is longer, you have to wait for a quite long period of time. From the perspective of the service provider, maybe the family doctor, well, they expect you to show up on the day of appointment. But in reality, what typically happens is that not everybody is going to be showing up, right? Well, people are busy. Maybe on the day of appointment, they have something else that is more important to them, so they fail to show up, right? Or maybe sometimes patient or customers simply forgot about their appointment and then they didn't show up. I mean, that may not be very common if we look at the records of a certain individual, but from the perspective of the service provider, this is not uncommon at all, right? So the problem here is that we want to predict a patient, or in other contexts, a customer will show up or not for his or her appointment, right? And that is quite important, because if I have reserved a time slot for a patient and that patient didn't show up, that is a kind of waste of your service capacity, your service resources, right? So I think we can all agree that this is somehow an important problem. Now let's load a data set and then try to look at what kind of information in the data set we can use in order to predict whether or not a patient is going to be showing up for his or her appointment, right? And to do that, let's again go to Avenue to Learn. If you log into your Avenue to Learn, and as usual, we go to content, the content section, right? And data set for in-class examples, they are alphabetically ordered. So this time we're going to use the first data set in this list. As usual, let me copy the link to the file in my GitHub repository. So let me copy link and then go back to Jupyter Notebook, right? So this is something we have been always doing. We're going to import pandas as PD in order to manipulate the data files and the data frame we import from the data files, okay? And then we're going to build a data frame based on loading this data file, right? So I'm going to call it APPTS for appointments, right? Short for appointments. So APPTS equal to pd.read CSV, and then copy and paste the link. Let's try to see if we can get a data file, right? So let's suppose that the loading will be successful, and then we're gonna check the first few lines of this data set. All right, so looks like things are working well here, and we can already see the first 5 lines of this data set, which contains records of patients. Right? Let's take a look at all those columns, but the very first 2 columns are just the IDs. Right? The first column is the patient ID, and the second column is the ID for the appointment. And those are just the identifiers of the records of the patient who made the appointment and the appointment itself. Right? As you can imagine, those first 2 columns are identifiers, and they are not of much value for predicting the outcome, whether a patient will show up for his or her appointment. Right? And gender, well, that may be something useful, right? Because maybe people of different genders may be different in terms of planning things, right? And keeping things in mind. Right? And appointment date, that's the date on which the appointment is scheduled. And appointment, there's a column which I call appointment DOW. DOW is a day of the week, right? So that's basically Monday to Friday usually, right? So, and then there's a column called lead time. Actually, we also had this similar term in the midterm test. Lead time means how many days we have between the day the patient requested the appointment and the day of appointment, right? So if lead time is 0 days, it means that I'm making an appointment for today, right? And it's for the second row in this data frame, the lead time is 35 days. It means that I'm making an appointment for a bit longer than 1 month later, right? So that's the meaning of lead time. And age is simply the age of the patient, right? And scholarship, actually I should mention that this data set is a real life data set from a hospital in Brazil. What they meant by scholarship is more like a welfare program, whether or not the patient is receiving some welfare assistance program from the government, right? So 0 means that the patient is not receiving financial assistance or social welfare assistance from the government's welfare program. 1 means that that patient is in this kind of programs. Okay? And then the next 3 columns, hypertension, diabetes, alcoholism, that means whether or not the patient who is making the appointment actually have one of those conditions, or perhaps more of those conditions, right? Hypertension, if you see a 0, it means that the patient doesn't have any hypertension condition. If it's 1, then it's the opposite, right? And same thing for diabetes, alcoholism, right? And handicap, that's basically an indicator of whether or not the patient have any disability. Again, 0 means no, 1 means yes. Right? SMS receipt, so basically sometimes they will send a text message to remind the patient of the upcoming appointment. Right? If it's 1, it meant that the hospital actually reminded the patient for their appointment. If it's 0, then no text message was sent. Okay? And then finally, we have the no-show result for those patient records. Right? This is very, clear. No means that no-show means that the patient actually showed up. Right? We say the patient is a show. If it's yes, it means that the patient is a no-show. He or she didn't show up for the appointment. Okay? So that's a quick discussion about the information contained in this data set. Okay? Do we have any questions? Well, because the data is from Brazil, right? So this you may have noticed that the spelling is a bit different from the typical English spelling. For example, hypertension, I think that's Portuguese. So just a side note, right? So I also explained those columns, those variables in the data set in details So later on, if you forget about the meaning, you can take a look. All right, so as usual, once you have the data set, we need to maybe look at whether or not if there's something wrong in the data set, like missing values, outliers, duplications, right? We can actually visualize outliers based on box plots. But to save some time, for now, let's skip those tasks. Instead, let's focus on one specific aspect. Right? We know that for the target variable no-show, we have yeses and nos. But how many yeses and how many nos? And that's something somehow quite important for classification problems. And we'll talk about why in a few moments. Right? So how do we find out the number of yeses and the number of nos for the target variable, which is the no-show column? What do we do? We need to do, of course, the data frame, right? And then we want to focus on the no-show column. Okay. I forgot if the no-show is actually, the show is capitalized or not. Let me quickly check. Okay, so small lowercase letter for show. And then we have this value count function. Right? So that counts the unique values in this column. Right? For nodes, we have 860 nodes, meaning that those 860 people, they actually showed up. Okay? For yeses, we have 245 of them being no-shows. Right? Yes means no-show, and no means showing up. Okay? What do we observe here? The main observation is that there's much more shows than no-shows, right? Which is normal, right? Usually people will show up. Right? In less frequent occasions, people forget or people are busy, so they didn't show up. But this may potentially create a problem for classification problems. So what do you think about some potential problems for this kind of records, which we call unbalanced data set, right? For the two labels, more no's than yeses. For those situations, one might possibly go wrong if we want to develop or apply a classification model to predict the outcomes. Any thoughts? Yes, please.
Obviously, if you could obtain the no-show, like when they, if you get some preemptive, if they're going to be, I don't know, sort of determination on cancellation, that could probably play into this a little more, because this is just no-show on the day of. You could probably have like another parameter that just captures was it cancellation and how many days before. You get a little bit of like a lead time on that.
You meant the lead time, how does that affect the results?
Yeah, for no-show at least.
For no-show, right?
Yeah.
But what is the problem of having much more no's than yeses? What do you think? Yeah, anyway, that was helpful. So yeah, lead time is going to be playing a big role, right? So, but imagine things like this. If you have one class label appearing much more than the other label, in the extreme case, things will be problematic. Right, so I have an example here. So let me see if I can identify it quickly. And the methodology we're going to use to address this issue is called resampling, undersampling or oversampling. But anyways, I would just want to quickly show you this example, right? So let's say we have another classification problem, right? There are two types of data points. Let's say we're gonna, in this case, we're gonna predict if a patient has diabetes based on the blood sugar level on the y-axis and the body mass index, right? I mean, as we can imagine, most people don't have it, right? So we have more blue points, meaning that the patient doesn't have any diabetes. Then those who actually have diabetes, star-shaped red points, okay? But what we care about when trying to do some classifications is typically want to be accurate, right? We said a patient doesn't have diabetes. We want my prediction to be correct, right? So that's related to accuracy. However, if we have predominantly a certain class label that's nose, let's say nose, okay, then potentially, regardless of whatever method you use, the algorithm can simply say that let's predict everything as nose, okay? So because that will help you achieve a high level of accuracy, right? There are 10 blue points here, 10 no's here, and 2 yeses here. What if I just simply choose to classify everything as no's, right? And then I get 10 correct predictions in this data set. I have 2 wrong predictions because I chose to predict everyone to not having diabetes, right? So I am correct 10 times, I'm wrong 2 times. So the accuracy level will be 10 out of 12, which is around, I think, maybe 83%, something like that, right? Which is already quite good for a classification problem, right? You can claim that, okay, I can achieve a high accuracy level of more than 80%, but your algorithm is going to be useless, right? Because you can never predict any patient who will have diabetes, right? So see the logic here? I mean, it's accurate, but it's useless, right? So that's something we want to avoid. And how do we avoid it? Well, let's look at a strategy, right? So this is just exactly what I just described. If you have predominantly many labels being one class and very few records belonging to the other class, and there's a problem, right? Because the model may simply try to predict everything to belong to the majority class, okay? So what do we do? Well, there are 2 strategies. This idea is pretty much the same. One is called undersampling, right? Let's imagine that we have 2 bins to keep the positive records and the negative records, right? So one of the classes is actually having more instances than the other, right? So let's say the majority class is actually negative, right? People are showing up, and the blue balls, they represent the positive classes in this example. Well, I want the outcomes or the labels in the data set to be balanced, right? One idea is that maybe I can simply reduce the number of instances belonging to the majority class, right? For the red balls, I have too many of them, so let's just draw a random subset from all those data points in the majority class, right? We had, let's say, 9 red balls representing, the 9 negative classes, right? And then we only have 5 records for the other class. So maybe let's just reduce the number of the majority class. Let's randomly draw 5 balls from the bin containing the majority class. And then we put together the original bin of blue balls, right? And then we also take the new bin of the 5 red balls, which was randomly selected from the original records of the majority class. And then we will have balanced records for each of the 2 classes, right? So that's one strategy. But what is some potentially damage or cons of this strategy? I mean, for sure it's useful because it really helps us resolve the problem of unbalanced data set, right? But there's some consequences. Right, so I mean, directly, the direct consequence is that we are throwing away some data points, right? So that's generally not a good thing because the more data you have, you tend to have better results in terms of the model performance, right? We always talk about big data. If you have a lot of data, it means that you can extract more information from the data compared with a small data set, right? So in order to address this issue, let's say we don't want to throw away data points. Maybe we can do the opposite, right? We have too few data points for the minority class. How about we try to increase the number of records in the minority class? How do we do that? It's similar, but also slightly different, right? Because let's say we have 5 blue balls and 9 red balls. If we use this strategy, it means that we want to get 9 blue balls from the 5 blue balls. How do we do that? As you can imagine, the only way is to create some duplications, right? This is sometimes referred to sampling with replacement, okay? The way it works is that, okay, let's randomly draw a ball from the minority class, the blue, the blue ball bin, and then let's say I got the blue ball with label number 1, okay? That's the first sample. Usually when we do sampling, if we take the ball with number 1 as the label, then that ball is gone, right? However, because we need to do oversampling, we cannot really get 9 balls from 5 balls. If every time we take away a ball, we don't replenish, right? So after taking away the blue ball with number 1, I will replenish this bin with an identical blue ball with the number 1, right? It means that we're replacing the original ball that was taken. Yes, please.
What is it better to duplicate versus imputing it with the mean or the median?
Well, imputing is that you have a few missing values. Usually there are those are just maybe you have let's say 100 rows, 100 data points, right? Some of them containing some missing values. I mean, maybe 5 of them. You have to impute them or try to throw them away. So then they don't hurt too much, right? But let's say in this case, we'll have a bit more than 200 for the minority class, but I want to repopulate the minority population so that I want to increase it to 860 records. If you do sort of imputing, that's going to be too much, right? Because you are adding so much noise. Imputing is not that reliable.
Okay.
It's just something we have to do when we have some missing values, right? So in this case, we want to get a lot of new records. The purpose is only to increase the weight carried by the minority class when you are doing the classification, okay? So this is called sampling with replacement. I take away 1 blue ball, labeled 1, labeled as number 1 blue ball, and then I have to replenish it. I replace the ball that was taken away by an identical blue ball, right? So that's why the second time I try to get a sample from this minority class bin, it's possible that I'll get number 1 again, number 1 ball again, right? Because I replenished it, I replaced it. And then I can keep doing this, right? I can take another ball, let's say number 3, and then number 4, number 5, number 5, number 4, number 5 again, because number 5, once it's taken from the original bin, it's gonna be replaced by exactly the same ball with the label 5, okay? So this is called sampling with replacement, and then by doing this, we can actually get 9 samples out of 5 original data points, right? And then I can do the same thing. I will put together those 9 blue balls, possibly, for sure having some duplications, right? And I'm gonna take all the other records in the majority class. I put them together, now I have a balanced data set, right? The only purpose of doing oversampling or undersampling is that I have similar sizes for the majority class and minority class, so that in the end of the day, when you're trying to apply the classification problem, those 2 classes should be carrying about the same weight, right? All right, so do we have any questions?
Yes.
Yes.
Can you explain again what you mean by replacement aspect?
Okay, yes.
Because I noticed that 2 is missing in the data set.
Oh yeah, so basically, it's very possible that you will have a 2 here, right? I mean, this is just an illustration. If you don't see a 2 here, it simply means that when you're doing the random sampling from the original thing of minority class, by chance 2 was not taken. Right? If I, by chance, get 2, right? A blue ball with number 2 will be here, and then I will replace that number two ball with a completely identical number 2 ball. So next time I try to draw another random ball, it can be this same number 2 ball that was already taken. Right? But it's also possible that it's not taken, because that's the idea of random sampling. Right? Everything is by chance. Okay. Any other questions? All right, so here are some discussions around, which method is superior. Actually, it depends, right? So because I would say that oversampling is somehow better, right? Because you're not throwing away any information in the data set. Okay? But sometimes you may want to do undersampling, especially for a very large data set. If you do oversampling, it will increase the whole data set size. Right? And then if you have a very large data set, things can get very slow for you to train the model on your computer. So depending on the computational power, you may want to make things easier. Right? Or you think that even though I'm throwing away some information by using undersampling, maybe that's okay, because I already have a very large data set. Throwing some of the data points away is okay. In those cases, that's also okay for us to do undersampling, right? One can also do hybrid sampling, right? For example, we have 200 for the minority class, 800 for the majority class. Let's say I want to get 500 for each of the 2 classes, right? And then I do undersampling for the majority class. I do oversampling for the minority class. In the end, I will be able to get 500 balls, which is in the middle between the size of the 2 classes, right, to form a sample that somehow trades off between undersampling and oversampling. Okay, so let's try to implement this idea of undersampling and oversampling. Okay, so to do that, let's try to separate the original data set. Right, so that's the original data set. So let's focus on the target variable, which is no-show. Okay, and then let's establish a condition to select all the no-shows. So that's the condition for me to tell if a record is a no-show record or a patient that actually showed up, right? So for all those no-show target variable equal to yes, I mean that patient is a no-show, right? And then I will include the name of the data set and wrap the square bracket around this condition. We know that that's called the filtering, right? That's how we select records satisfying a certain condition, right? And then I will just say those are the appointments of no-show patients, right? So let's call it APPTS no-show, okay? And then I can do exactly the same thing. So let's copy this line of code. But this time I want to create a data frame that only contains the patient records who eventually showed up for their appointment, right? I only need to change the value, the target value to no, right? So this second line of code helped me build a data frame that includes all the records in the original data set for which the patient actually didn't do no-show. In other words, they actually showed up, right? So let's try to run the command, and it's done. All right, so then we want to focus on one of the classes, show or no-show, right? So let's actually do oversampling, right? So let's actually focus on the no-show class, because as we recall, there are fewer data points for the no-show class, right? Only 245 patients have the label of being a no-show, okay? So now we can do the sampling, right? Regardless of using whether or not we want to use oversampling or undersampling, it's the same function, right? It's df.sample. df represents the data frame you want to use. Okay, and dot sample means that you are taking samples from that data frame. And there are a few keyword arguments important for our purposes. And let's do this command to see how we can specify those keyword arguments to control things. Okay, so now I want to focus on APPTS no-show, right? Because I want to do oversampling for the no-show class. Okay, dot sample. The first thing I want to specify is how many samples I want to, how many data points I want to use to form the sample, right? So that's because we're doing oversample, so we need to do the number of data points that is exactly or at least close to the majority class, right? So let's do n equal to the length of APPTS show, right? So that will give me the length of the patient who actually showed up, right? And that should be actually 860, right, if you still recall. And then, actually, let me make it, sorry, and show, right, to make the meaning more clear. Right? And then I will specify for doing the sampling, n representing the number of points I want to get from the data frame, n equal to n show, right? So that will give me exactly the same number of data points as the majority class, people who actually showed up, right? And then the second keyword argument is replace equal to true. Because we're doing oversampling, we have to do replacements. Otherwise, we cannot get more data points from what we originally had, okay? And then there's the random state. Random state, let's equal to 42. I mean, you can do any integer number, right? So it doesn't matter. It's just for being reproducible, right? Next time we want to run the same command, you want things to be exactly identical so that you have more control, or you want to know if there's an error, what has gone wrong. That's the purpose of doing random state, right? So that will give you the oversampled no-show data points, right? So let's call it APPTS, and again, no-show, maybe OS. It's getting a bit long, but you know, to make the meaning clear. So this is the oversampled data points for people who turned out to be no-shows, right? And then we can run this, and eventually we also let's first run it. So there's no actually error. That's good, but let's try to confirm things. APPTS no show oversampled, right? Let's look at the shape. Well, we have 860 rows and 14 columns. And the 14 columns are just all the columns in the original data set. And then if you remember the majority class, people who showed up, we had 860 data points there, right? So now after sampling, you know, the no-show parts of the data set, now we also have 860 records that has the label of no-show, right? So questions? All right, but that's not the end of the story, right? Because we separated the two parts, and then we oversampled the minority class part, right? Now we have two separate data, data frames. We have to put them together, right? So this is something we didn't talk about before, but it's also a very useful technique for manipulating data frames. Right? So this method is for concatenation. What does it mean to do concatenation? Well, there are two ways of doing concatenations for two data frames, right? If we look at the figure on the left part of this screen, right? So in this figure, we are doing some vertical concatenation, right? Or sometimes we say concatenation along axis 0. Axis 0 is the vertical axis for data frames, right? It's very easy. We just vertically put the two parts together, right? And this is as opposed to the other method of concatenation, right? We have two data frames. If we horizontally combine them together, so that we will have more columns than the original two data frames, and then that's called horizontal concatenation, right? Well, the important thing is that if we're doing vertical concatenation along axis 0, we must have the same number of columns for those two data frames being joined together, right? And then we need to have same number of rows if you are concatenating along the horizontal axis, horizontally. Okay, so by default, it's actually always to join things together along axis 0 if you don't specify the direction. So let's do this. We're going to do pd.concat. So that's PD is for pandas. So that method will help me combine the two data frames. So remember, we created two smaller data frames. One is APPTS, no show, and then OS, meaning oversampled, right? So that's the oversampled data frame with no show records, but we increase the size, right? So in this list, we need to also include the other data frame to be joined, okay? So this is going to be APPTS show. And then by doing this command, we're putting the two data frames together vertically, right? You can do axis equal to 0 to specify the direction for joining the two data frames, but by default, it's already axis equal to 0, right? So after joining them, we need to give a name to the combined data frame. So let's still call it APPTS to override the original APPTS, because we'll be no longer using the original data frame, right, from this point on. So let's take a look. Okay, and then we can do APPTS.head to see the new data frame, right? But one thing we observed is that, well, the row indexes seem to be a bit messed up, right? Because remember what we did is did some random sampling, and then after we did some random sampling, we put the two data frames together. So the indexes are just the indexes from the original two data sets. They're messed up because you did some scrambling when doing the random sampling for oversampling, right? So it's generally a good idea that we ought to do APPTS.reset index. Right? After you have reset the index, and then we'll have index starting from 0 and increasing continuously, right? We have to do drop equal to true, because if we are resetting the index, we want to drop the original index, right? So, and we also need to do in place equal to true, because I want to have the APPTS data frame to be changed after I reset the indexes, right? I mean, not changed for all the data fields, but only for the index part. Okay, so let's try to see. There's some, I think, sorry, I forgot. There's no score between in and place. Okay, so this looks a bit nicer, right? Because notice that the row indexes are not looking correct. Okay, well, if you want, you can actually check. The value counts for counting the target variable class labels, yes or no. And I'm going to skip this for now, but if you run value counts on this column, you will find 860 instances for both type of patients, show or no show. Okay. All right, so that's a bit of pre-processing before we start to build the classification model. Okay, and it's about time for us to have the first break, so I will pause here. Let me know if you have any questions, and we will come back in 10 minutes at 12:30. And feel free to do some stretching or get some food.
lines of code. I've got
Oh, I see. You shouldn't use dot because in Python, dot is reserved for the attribute or method belonging to a certain object.
Okay, so
Yeah.
what should I
Use
here?
the. I think underscore is more
Underscore?
common. Yeah, yeah. You can use anything. You don't have to include anything.
But still.
Okay. Yeah. It says a must be greater than 0 unless no samples. Let me take a look.
Is there something wrong at the above code?
Place. This seems to be okay. No show dot sample. Okay, so can I see it again?
Yeah.
A must be greater than 0 unless no sample. Okay, yeah. N equal to number of no shows length. Show. Can you scroll up a little bit? This seems to be okay. Show and no show. This is okay. Sample. Might be strange. Can you also include this variable at the end of the line? Let's check what is the value of this variable.
This one?
Yeah, change. Yeah, this one exactly. And go to a new line. Maybe use a return to get a new line.
Okay.
Yeah, and then can you? Sorry, let me move things a bit.
Maybe use hat.
Yeah. So
Okay.
just no of show so no of show, number of show.
Show.
Yeah, run it and let's see what's happening. Okay, this seems to be okay.
Yeah.
That's a bit strange. Invalid weight sum to 0. So I didn't have this actually. Sample. Yeah, let me look. Let me just compare what I have here. Yeah, so this seems to be the same, right?
Yeah, it's from the
Sample n equal
I
to
literally just
number show.
copied that.
Yeah. Yeah. I mean, it's the same. I don't know why. Can you then? I think maybe it's something like. That's a bit strange. So, can you show this APPT appointments no show?
Okay, maybe.
Yeah, maybe add a new.
Yeah.
Yeah. I want to see what's there. No show.
Show.
Yeah. So let's see
Run
what's
it.
up.
There's no.
Oh yeah, that's why I
value
guess.
here.
Yeah, maybe let's go back to the original case. No show. I see. You should capitalize this yes, right? It's a very small thing. It's a,
Oh
yeah, it's
Here.
I mean,
Okay, okay,
Yeah, that's right.
wow.
There's no small. I mean, sometimes it happens.
I'm
right, because,
gonna try this again. Okay, here it is.
Yeah,
Okay,
yeah.
thank you so much.
Okay, you're welcome. Okay, it's 12:30. Let's get started again. So before the break, basically, we were doing some pre-processing. One thing we did, the most important thing we did is to do oversampling for the minority class, right? So let's just quickly check that now we have a balanced data set. So the data frame, and then focusing on the no-show variable dot value counts. Okay. And then we can see that the yes labels and no labels, each of them having the same number, 860 records in the data frame. Right? And that is good because that's what we wanted. Right? We wanted to have same number of yeses and nos so that we have a balanced data set with respect to the target variable values. The next thing we're going to do is to do some feature scaling. What does it mean to do feature scaling? Okay. Actually, let's look at two particular columns as an example to perform feature scaling. Okay. Well, let's focus on this column of lead time, another column, the age of the patients. Right? So one thing that always happens is that for different features, they have different scales. Right? By this, I mean that the range of possible values of lead time is going to be different from the range of possible values for ages of patients. Right? And let's quickly try to visualize what I meant by having different scales. I mean, the concept is not difficult, but it's easier if we do some visualization. So let's import matplotlib.pyplot.splt, and then we're going to create a box plot. Box plots are particularly useful for situations like this to compare the distribution of values for two different or even more variables, right? So I'm going to include two columns. One is the, as we said, lead time. Right? When you are typing, be careful, with the upper and lower cases of the variable names. Sometimes a small error can just get the whole thing stuck, right? So this is something we have done before, right? Just include the two variables, two columns in a list and feed it to the boxplot function for matplotlib. Right? And then we can look at the result, right? To make it nicer, we can do plt.xticks. The ticks are currently 1 and 2, right? So we want to rename them to the names of the columns. All right, so we see that the lead time basically has a large range, but there are many outliers. Most of the probability is concentrated within the box. That captures, I think, from 20% to the 75% percentile. That captures half the probability. And then there's some small probabilities captured by the two whiskers. Right? If we compare the height of the two boxes, we can see that, well, age variable in this data frame actually has a wider range. Right? Also, age tends to have a higher median or average compared with lead time. Right? This means that they are different in terms of the range of their possible values and distribution of their possible values. Right? Sometimes we say this is different scales, which is expected because they are very different quantities. Right? And different scales for different variables sometimes creates a problem for machine learning problems. For logistic regression, I would say generally it's okay. It doesn't affect too much, right? Because remember, the features are multiplied by their coefficients. Right? If the scale of features is larger, the coefficient is going to be smaller, but that's not too much of a big problem. And later on, when we talk about other classification problems, methods, like k nearest neighbors, that's going to be a huge problem. However, even though it does not affect too much, still, it at least affects the performance or efficiency of the algorithm. It may run slower, right? So for age and lead time, they have different ranges. If we want to sort of convert those two variables into two new variables so that they have similar ranges and similar scales, and then something we can do which is called standard scaling, which is not the only way of doing scaling, but let's get started from this particular most commonly used scalar, which is called standard scalar. How does it work? So let's look at age column. And if we look at the age column, I just simply took that column, put it here in this figure. So this is just a list of numbers, right? And for list of numbers, we can easily calculate the mean value and standard deviation. Right? So the mean value turned out to be approximately 36 for this age variable. Right? So on average, patients who visit the hospital, they are 36 years old. I mean, of course, some are older, some are younger. Right? And the standard deviation is 22. It's quite variable in terms of the standard deviation. The idea of doing scaling is that I want to subtract the mean value from all those numbers. Right? If the mean is 36, it means that for every single number here, I want to subtract 36. Right? For first age 0, that's a newborn baby. So I'm going to do 0 minus 36. The second patient, 66 years old, again, I'm going to do 66 minus 36. Right? And then for every single patient in this data set. After that, we also need to divide by the standard deviation. Right? So the first number 0 minus 36, subtract the mean, then I will divide that by 22. And same thing for all the subsequent numbers. And this is called the standard scalar being applied to a column of numbers. Right? And typically, we want to apply the standard scalar to several columns in the data set. So that after performing the scaling, all those variables will have a similar scale. Right? The range of possible values now look more similar than before. And that is the main purpose. Okay? Do we have any questions? As mentioned, why do we scale the features? Well, for logistic regression or even linear regression, that makes the algorithm a bit more efficient. So the learning will be faster. For other methods, especially the distance-based models like k nearest neighbors, this is very important. You cannot just go anywhere without doing scaling. Okay, and we will, when we talk about k nearest neighbors, I guess next week, we'll expand on the point on the importance of scaling for those type of methods. Okay. So we talked about the main idea of doing standard scaling, right? Subtract mean divided by standard deviation for every single column you want to scale. But how do we implement it? I mean, it's not too difficult to just subtract mean and divide by standard deviation. But there's actually a function that already implemented the standard scalar in the sklearn library. So for simplicity, let's just apply the existing Python function from sklearn to the columns we want to standardize. Right? So let's take a look at the table again, the data frame again. Right? So this time, let's only scale lead time and age. Right? So in this example, we're only going to focus on two columns, only lead time and age. Other than those two variables, well, we have some categorical variables. We also have some 0, 1 variables, which is essentially the same as categorical variables. We don't want to, for now, at least for this method, logistic regression, we don't want to standardize those 0 to 1 columns or categorical variables. Why is that? If you really want, you can do that. There's no much harm coming out of that. Right? But maybe we don't need to do that for logistic regression. Why is that? Well, because they have nice meaning, right? 0 and 1. 1 means, let's say the hypertension. 1 means the patient has this condition. 0 means that the patient doesn't have this condition. So it has nice meaning. If you apply the standard scalar, things will become very messy, right? The zeros and ones are again replaced by some seemingly very random ad hoc numbers, which does not have particular nice meanings like the original values. And also for those 0, 1 binary value columns, well, the scale isn't too large, right? I mean, after you perform standard scaling to certain variables, you will have 0 mean and standard deviation equal to 1 because you subtracted the mean from the original column, so the mean becomes 0. You divide the standard deviation, so the new standard deviation becomes 1. So it's not too different from the binary valued columns in terms of scale, right? So let's only focus on lead time and age for this data set when using logistic regression, right? Later on, when we talk about k-nearest neighbors, we actually need to standardize or scale those binary valued columns. Right? And let's see how we can do this. In order to apply the standard scalar, we actually need to do several things, all right? So one thing we need to do is I think it's a good idea to first try to specify the features to scale, okay? Features to scale. And that's for now, that's gonna be a list of two feature names, lead time and age. So this is simply a list of strings, right? So we want to specify the names of the columns we want to scale. All right. After doing that, let's also import a module from sklearn. The module is pre-processing. Right. So because like over undersampling. Or one-hot encoding, this is one of the pre-processing methods. From this module, we're going to import standard scalar. Okay? And then the first step is to create an instance of the standard scalar. So I'm going to call it just a scalar. Scalar equal to standard scalar. And that's a function, right? It does nothing but just to tell you that we're going to apply the standard scalar to some columns of the data frame, right? I mean, we didn't specify anything. It's just creating the method as an object, okay? So that's the first step. The second step is that we're going to provide the necessary information to this scalar we created, right? Because we want to scale the two columns, lead time and age. Right? I mean, in order to apply the scale, you can imagine that we need to tell the scalar to subtract the mean and divide by the standard deviation of those two columns. Right? We didn't need to do too much. We want to do one thing, which is to fit the scalar to the variables of interest. Right? So the way we're going to do it is that there's a function that comes with this scalar object called fit. I'm going to fit the scalar to the variables of interest. So the input argument of this fit function is going to be the corresponding columns. Right? It's actually lead time and age, but this time I can just do features to scale, right? Because features to scale is already the name of the two features I want to scale. Putting it between these pair of brackets is the same as specifying the two columns, right? So then, if I apply this, I fit the scalar to the columns of interest. And effectively, that's actually telling scalar about the mean value standard deviation of those two columns. And later on, in the third step, we're gonna transform the data, right? Once we have fitted the scalar, we're gonna use the scalar to transform those two columns. So here comes another method, which is simply called scalar.transform. And the two variables I want to transform is again the two columns, lead time and age of the original data frame. So I'm just gonna copy this appointments features to scale again, right? So this argument inside the round brackets is simply the two columns, lead time and age, right? And then I provide those two columns to the scalar, which has already been fitted according to the information contained in those two columns. And then I transform it. After I apply the transformer function, what happens is that it will actually return two columns that contain the scaled values of the original two columns, right? So I need to store the output from this transformation function. Let's call it features scaled. Right? So let's quickly overview the steps we went through. First, define scalar, and then fit the scalar to the two columns. And third, use the fitted scalar to transform the two columns, and the output will contain the scaled values. Okay, and after that, this feature scaled are the scaled values of those two columns, right? So let's actually do one more thing. So let's take this appointments features to scale again, and assign the output from the transformation to overwrite the original two columns. In that case, the original two columns will be replaced by the scaled columns, right? And hopefully things will run smoothly because it's a relatively long block of code. But after we have finished executing all those steps, I want to quickly view what's happening in the scale data frame for those two columns, right? So let's try to run it. It is done successfully, but let's take a look at what's happening, right? Nothing much has changed for any column not involving lead time and age, right? But for lead time and age, for those two columns, as we can see, it's no longer the original values, right? I mean, it's now looking very small numbers, which is the point, right? Because we subtract the mean value divided by standard deviation. So it should be something like the normal distribution with 0 mean and standard deviation equal to 1, right? So we have seen some very small values centering around 0, right? This is the purpose. So things are looking okay, but do we have any questions so far about scaling those two columns? Things are okay? So again, the key idea is that we define a scalar, tell the scalar to fit and transform those two values, right? And the outputs from the scaling will be two columns with scaled values. I just assign it back to the original columns. So the original two columns got replaced, right? So now we need to move on, but before moving on to the learning model, let me go back to the box plot because I want to do exactly the same thing again. But now I want to see what has changed for those two scaled features, right? So in terms of the codes we're using, it's exactly the same as the box plot we just created a few moments ago. But now let's look at what has happened, right? Well, again, two box plots. Remember, originally the age column, we have a larger mean, right? The box is moved toward the top of the plot compared with the lead time column, right? And it's more spread out than the lead time column, right? But now, I mean, they're still different. You cannot, hope to have exactly the same range or spread for those two variables, even after scaling. But now they are much more comparable than before, right? So, well, at least the height of the two boxes are now very similar, and the median values are also roughly the same, right? Not exactly the same, but roughly the same. And the mean value is not shown here, but they should be both equal to 0. All right? So this is the purpose of doing feature scaling. It's a good idea to put everything on the same scale, so the range may look somehow similar. Right? So that's one step you always want to use. It may or may not improve your performance for methods like logistic regression, but you should at least try it out to see if you do scaling, does it help? Right? If it's not help, you can always go back to the original data set without any scaling. All right, so one last step of pre-processing, which is one-hot encoding, right? So let's do appts.head. Okay. And there are some categorical variables. So like appointment day of the week, Monday to Friday, I suppose. Right? And then all those scholarship, hypertension, they're already binary value. We don't need to, they're actually also categorical variables, but it's already encoded using binary values, so we don't need to do anything about them. Right? And we also need to do something with the no-show column, right? Because it's yes and no. In order to apply machine learning algorithm, we generally prefer to use 0 and 1. Right? So we need to convert the last column, the target variable, from yes, no to 0 and 1. And let's first deal with the last column. To do one-hot encoding, we can just use PD pandas.getDummies as what we have done for linear regression before we did the midterm, right? But for the last column, no-shows, let's actually use an alternative method, which is called mapping, which is similar. If you want, you can actually use get dummy variables for the last column. But here, let's just take this chance to get a new method, right? So I'm going to focus on the no-show column, the target variable. And then I'm going to define a map. And the argument to this map is a dictionary. And dictionary is perfect for doing mapping because it maps some index value to some numerical value or a non-numerical value, right? So the indexes will be yes and no. And then I'm going to map yes to 1, as usually is the case, right? And no equal to 0. So intuitively, by applying the map function, I'm mapping yes to 1 and no to 0 for the last column of no-show. And then this will convert to the target variable to 0 and 1 values. I'm going to assign it back to the original data frame column no-show. Right? So that's going to overwrite the last. The original column of no-shows, yes or no, now it's going to be 0 or 1. Okay, let's do that. Now we see that for the no-show column, the yes values have been replaced by ones. If you have a no value, it's going to be already replaced by zeros. Right? So that's an alternative way of doing one-hot encoding if you have yes or no. True or false, or positive or negative, those kind of things, right? And then, what do we do? Actually, there's only one thing we need to do for one-hot encoding, right? Because the only 2 categorical variables here seem to be gender and appointment day of the week, right? I mean, the IDs are not important. We're not going to make use of the IDs. They don't contain any information. Right? We're going to throw away the IDs later when defining the features. And gender, female, or male, and let's convert that to 0 and 1 using dummy variables. Appointment date, that's a date-time format. It's also not going to be much of use since we are going to rely more on the lead time column, right? So after in the original data set is also the neighborhood information where the patient lived. I throw that away because it's a bit cumbersome, and I find that it doesn't affect too much about the performance. Anyways, so let's perform the one-hot encoding to encode the categorical variables. Okay. So to do that, we're going to do pd.getDummies, right? That's something we also did for linear regression before our midterm, right? And then I'm going to provide appts as the original data frame for which I want to perform one-hot encoding, right? If you just stop there, then it will encode all the columns of the data type being object, right? But I don't want to do that because patient ID and customer ID or appointment date, those are also seemingly categorical variables, but I will just choose to not doing anything to them, right? Instead, I'm gonna specify the columns on which I want to perform one-hot encoding. And those are gender, as we mentioned, right? Gender, appointment, DOW, day of week, right? Monday to Friday, I guess. Okay, so this means that for this data frame, for those two columns, we're going to perform one-hot encoding. For the remaining columns, just to keep them the way it was, okay? Not doing anything to the remaining columns. But remember, we have several important things to do for one-hot encoding. Typically, we want to do drop first equal to true, right? Because gender, male or female, I only want to, let's say, indicate if the patient is a male patient or not, right? And that already contains the information for the patient being female or not, because suppose that there's only two genders, which is the case in this data set, okay? Okay, then D type equal to integer, int. Right? Otherwise, you would get true and false for the one-hot encoding, but we want to get 0 and 1s, right? So this is the method, and it will get us a data frame with all the specified columns, gender and date, appointment day of week, encoded into 0 and 1, okay? And then I'm gonna assign it to a data frame called appointments encoded, okay? And then before running the command, let's take a peek at the first few rows by using the head function, all right? So, most of the columns are not changed, but we do see the appointment day of week being encoded into several columns, right? And we also have the gender. Now it's encoding gender being male. Is it true, right? For every patient, 0 means that it's a female patient. 1 means that it's a male patient, okay? Anyways, this is the encoded data frame. That's something we have done for linear regression as well, right? Let me know if we have some questions. Now, if not, now we're ready to proceed to the logistic regression model. So we have done all the important pre-processing steps, oversampling, and then we did feature scaling, and then one-hot encoding. Now finally, we have the encoded data set on which we want to perform some classification, right? And again, this is the logistic regression model, how it works mathematically. Not that important, but the important thing is that in the end of the model fitting, we will let the model tell us about the intercept and the coefficients for those features, right? Because they indicate how important are those features. If you change a certain feature by a certain amount, how much would you expect the final outcome to change? Right? And that's the most important thing to keep in mind in terms of how mathematically the model actually works. Okay, okay, so remember, if we want to do prediction, just like linear regression, we need to separate the data into the target variable and the features. In other words, usually we use X for features and Y for the target variables. Right? And then we want to let the model establish the relationship between X and Y based on what it has observed in the data set. And let's just do that. Okay. So what is the function to use here in order to split the data set into X and Y? Well, actually, not quite so at this stage, but then we need to define X and Y, right? So X is going to be, now we focus on the encoded data set, okay? And then we're going to select the features we want to use to make the prediction, right? But then we can select all the features, but it's more efficient to just drop the features we don't want, okay? Because one thing, obviously we want to drop is target value, right? Because that's the target should be included in the Y part instead of X part, right? So let's drop no-show. And then let's also drop some of the less important things like patient ID. In this data set, pay attention, I is capitalized, D is small letter, lowercase letter. And also appointment ID. So appointment. And this time ID are both uppercase letters. And there's one more thing we want to drop, which is appointment date. Appointment day. And that's the date time format, like, month, day, and the year. But that's not too important because intuitively it doesn't provide any meaningful interpretation other than, unless you want to, apply the day and month, like let's say in winter the no-show rate is higher, that's also possible. But for now, let's not use this information for the purpose of just demonstrating this method, right? And then we're dropping the columns. Whenever you're dropping the columns, specify access equal to 1, right? Because access equal to 0 means that you're dropping rows, okay? And then let's drop those, and then the result will be assigned to X. After dropping the target and the irrelevant information from the data set, we get a feature set, right? And then Y is equal to, again, APPTS encoded. And this time, only do the no-show, which is the target variable, the variable we want to predict, right? All right, so let's run those. No error, that's great. So we have X and Y. That basically separates the target from the features, okay? And what's the next step? Well, we can predict Y based on X, but remember, it's always important to do the split of both an X, Y for creating, the test data set and the training data set, right? When we ask the model to learn the relationship between X and Y, we will let the model only use the part from the training data set. Right? And the test data set is typically reserved to simulate the future. Right? That's the part of data not seen by the model. So it's the future, in some sense, to the model. Because the final purpose of our prediction is about predicting the future, right? We need to have some idea from the data about the accuracy or performance of the model. So again, we need to import a module, and this time it's the model selection module, and we want to include the train test split. All right, so we want to import this method in order to split the both the feature data and the target data into training set and testing set. Okay, so then we can do X train, X test, Y train, Y test, and those are the outputs from the train test split method. And then let me copy this train test split. I want to split X and Y, right? I want to split both X and Y. And then a few keyword arguments, not required, but it's a good idea to specify. Otherwise, the default value will be used. Text size is 0.2, meaning that I'm reserving 20% of the data set as testing data set, right? 20% of the rows are gonna be used as the test set to simulate the future. Random state, right? Random state for reproducibility. So again, let's do 42. You can use any other numbers, right? And I'm gonna do one thing. I put it here. Stratify equal to 1. Y is the target variable. So can you guess the meaning of this particular additional keyword argument? Stratify equal to y. What can it possibly do? Well, remember, there's something important, right? We said that we need to have balanced data set for classification problems. We don't want to have a majority class and minority class that differ drastically in terms of the number of instances they include. Right? This is already achieved in the original data set after performing oversampling. Right? That's the purpose of doing oversampling. But now you are splitting them, and the splitting is randomized. So potentially, it's technically possible that after splitting, let's say focusing on the training data set, after splitting, you introduced some level of imbalance into the data set, right? Because originally it's balanced, now you are randomly split the two parts. Now each of the part, possibly they're no longer balanced, or at least less balanced, right? It's not a big deal because, well, if you have a large data set, you are doing random split, the chances that usually it's automatically balanced, right? But just to make sure that we still have a perfectly balanced data set, after doing the splitting, let's specify stratify equal to y. It means that we're going to look at the labels in the target variable y, and after splitting, I want to have balanced 0 and 1 for the no-show column as the target variable, right? So that's the meaning. So let's just run this, but after running this, let's actually take a look at y-test. I mean the test data set of the target variable after splitting. Right? And then it's a pandas data series, only one column, but it's very similar to a data frame. So let's just do value counts on the y variable to see whether or not I have balanced 0 and 1s, right? So let's run this. Okay, doesn't work so well. Actually, a typo. Sorry about that. All right, so this completes the splitting, and then after using the train test split function, the final line basically checks the value counts for the test part of the target variable. As we can see, 0 and 1 are still balanced. That's because I specify stratify equal to y, so that I want to focus on the target variable, make sure that things are still balanced after I split the data set into training set and testing set. All right, so questions? Everything okay? Okay, great. So now, now we can actually start to do the logistic regression part after we get the training set and testing set, okay? So actually I believe I have already done this part. So I'm gonna skip the screen because it's already done on the previous screen. Now, let's train the logistic regression model. So again, we need to import a library for defining the logistic regression method, right? So it's gonna be from sklearn dot linear model. I mean, we use the same module for linear regression, but logistic regression is something we consider as generalized linear model because the decision function is also a linear function, right? So it's in the same module. From that module, let's import logistic regression. Okay? I capitalize L and R for the first letter of the two words. Okay? And then after I get this function, logistic regression, to create the method, I will create a model. Okay? And I can call it model. I mean, if you want, you can call it like logistic regression model or any name you want. Just remember that the name of the model you created. Here, for simplicity, I'm just calling it a model. Okay? Because for now, we're not doing any other models, so just call it a model. And this model is equal to logistic regression. You know, this is the method we just imported from linear model module. Parentheses for functions. Right? After I create the model, then immediately I want to fit the model. So model.fit, and from X train, Y train. Right? Well, this is very intuitive, right? I build the model, and then I ask the model to detect or learn the relationship between X and Y, but only focus on the training data set. Okay? So let's run this command. You see this blue box or blue table. I mean that it's actually already fitted successfully. Okay, so the model has been fitted. I mean that, remember the mathematical part, the coefficients and intercepts, they are all already been obtained. Now, we will be ready for doing some predictions. Okay. This time, we're talking about predictions. Right? There are two ways of making predictions for classifications. Remember, when we started with logistic regression, we already mentioned that this is a method based on predicting the probabilities. Right? I see a new patient record. Is he or she going to be a no-show? Well, we cannot be 100% sure usually. So we only try to guess the probability of the patient being a show or a no-show. Right? So in order to make predictions, we're going to first do the probabilistic prediction. And then we already have the model defined and trained, right? And then we're going to let the model to make some prediction. Model.predict. And then underscore probability. But I mean, the name of method only include the first 5 letters of probability. So model.predict proba, and that's going to be predicting the probability. Of course, I need to supply the new data points to this function to make the prediction, right? I mean, we can define a new patient by looking at the information regarding things we included in the original data set, like age, lead time, how early did the patient made any made the reservation or appointment, right? And then the medical conditions. But for simplicity, let's only do one thing here. Okay, let's only predict on the test data set. Right? Because in the test data set, X includes the features of the patients included in the test data set. All the features has been included. Of course, we already know the outcome for the test set, but the purpose is that we pretend we didn't know, and then look at the features of the patients in the test set, try to make predictions, and compare the prediction with the actual observations to have some idea about the accuracy of the model. Okay, so let's do this, and then the output is going to be some predicted y. So let's do y prob equal to the prediction outcome, right? I mean, just to represent that it's a probabilistic prediction, and then what we can see the probabilistic prediction from this model. Okay, so we can see it's actually a 2-dimensional array. It's like a table or like matrix, right? It's a bit overwhelming, so let's only look at maybe the first 5 rows from 0 to 5. So those are the outcomes of the prediction performed for the first 5 patients in the testing data set, right? And then we want to interpret. So how do you interpret those numbers? We have an array that has 2 columns. Remember, we have a binary classification problem, right? So in other words, for every patient with some given features, what we're doing is to predict the patient to be a no-show, and equivalently predict the patient being a show, right? So we have the probability of the patient showing up or not showing up, right? So let's look at the first row in this prediction outcome. Okay. There are 2 numbers in the first row. I mean, for every row, for every patient in the test set, we have 2 probability numbers. Right? For the first row, it's about 0.58. And that's the probability of the patient being a 0. Right? It starts from 0, the first column is 0, the second column is 1. And 0 means that it's not a no-show, it's a show, right? So the second number in every column represent the predicted probability of the patient being 1, and 1 is no-show. Right? So the way we interpret this result is that for the first patient with the given features in the data set, the probability of the patient being a no-show is about 42%, right? 0.4223. So that's the mean. And the other number, 0.58, that's the probability of the patient being a show, right? The probability of the patient to show up on the appointment day. Okay? So that's the meaning. And we can simply interpret every single row in this output array in a similar way, right? So every record, every row is the prediction outcome for a patient in the test data set. There are two numbers. They always sum up to 1. The first number is the probability of being 0 or negative or not a no-show, right? The second number is the probability of being no-show. So that's the probabilistic prediction. Questions? All right, so this is just exactly what I just explained. All right, so there's another way of making prediction. Right? Sometimes I just need the information from the decision maker. So tell me whether you think the patient is going to be a no-show. Right? So it's very similar. Let's create another variable, xPredict. xPred means the prediction, right? And this time let's do deterministic prediction. So model.predict without the probability part. It's exactly the same if I want to predict on the test data set. Okay? And then let's do this, and then I will again look at the first 5 rows, for first 5 predictions for the test data set. One error. Again, due to a typo, sorry. Right, so this time I excluded the probability part, right? Directly let the model to make prediction on the test data set. Then it gives me 0 and 1s, right? The first 5 predictions are 0, 0, 1, 0, 0. So only the third patient in the test data set among the first 5 patients will be 1, will be a no-show. The remaining patient will show up. Of course, that's just my prediction. May not be true in reality, right? Or compare with the actual observations, the test data set. Okay, so that's how we make predictions. But then the question is, how did we convert the probability into those deterministic predictions? Actually, we mentioned that last time, right? If the probability of no-show is high, then we predict that patient to be a no-show. By default, the threshold is 0.5. If I predict based on the feature of a patient, the probability of that patient being a no-show is 0.6, let's say, then it's greater than 0.5, then I predict that it's a no-show. Okay? That's how it works. Now, before the second break, let's talk about a different way of making deterministic predictions. Well, because sometimes you may think that the threshold of 50% or 0.5 as the probability of no-show being too aggressive or being too conservative, depending on your purposes, right? So let's say I want to be conservative in predicting no-shows. Right? I'm reluctant to predict a patient to be a no-show if the chance is 50-50. Right? I want to be more conservative. Then what do we do? So for example, let's do y-prob. Let's simply look at the first row, right? So the probability, maybe just to do, anyways, let me just do everything, okay? It's a bit cumbersome. But then, you see, maybe I'm reluctant to predict a patient to be a no-show if the probability of no-show is above 50%, but not too much, right? So in that case, what I can do is that I can define a threshold. So let me define a threshold, which is different from 50%. Let's say 60% is the probability threshold for predicting no-shows, right? And then what I want to do is to check the second column of this probabilistic prediction outcomes. So I'm going to do something called slicing we did in the beginning of the term, right? So all the rows, I take all the rows, but only focus on the first column. So I'm only looking at the second column. Actually, sorry, 1 being the second column. This column is the probability of being no-shows, right? And then I want to see if those probabilities in the second column is greater than the threshold. So let's see what happens, okay? So now we can see it has been converted to true, false values. So the first record in the test set, the first patient in the test set is false, meaning that it's not, the probability of being no-show is not exceeding 60%, 0.6. And the second one is also false. The third one is actually true, and so on and so forth. Right? Of course, that's just the true-false predictions. It tells us whether or not it exceeds the threshold. But then what I want to do is that if it exceeds the threshold, I want to predict that patient to be a no-show. Otherwise, prediction is that the patient will show up, right? So what we can do is that we can further convert the outcome of these predictions to be 0 and 1 values. Okay, so let's see how we can do that. So this is the column numbers. So let me quickly check how to do that. So I think it's just to do, let me try to see this. I don't remember exactly. Yes. Okay. So I take the true false values and then I convert them to integer values. So convert them to the type of integer. So then I convert false to 0, true to 1, right? I mean, if we have a true, it means that the probability exceeds 0.6. And then I convert to 1, meaning that I think given the threshold, the prediction is going to be a no-show. Right? So that's how we can make predictions in a more customized way. Right? So we can assign it to y, let's say, customized prediction. Okay? And then we can, there's a lot of numbers here, but let's just do the first few, 0 to 5. Okay, so that makes the predictions for the first 5 patients in the test set, right? I mean, not too much different, not different at all compared with the default prediction for the first 5 patients, but for the remaining records, it's gonna make some difference, right? If a patient has a probability of being no-show very close to 50%, maybe slightly above, and we still predict that patient to be showing up, right, according to the customized threshold value. Okay, so do we have any questions? Okay, let's have the second break. Sorry, it lasted a bit longer. Let's come back at 1:33, but we're still gonna be finishing on time, even though we started the second break a bit later. Yeah.
I have a question. So
Yeah,
I'm getting a lot of errors,
Okay, yeah.
and I think
Let's see.
I think the reason why is up here. I'm getting the no-show as not a number.
Oh, I see. Can you go? Let me see. No show. Okay.
So what I did was I did this and it worked, and then I just changed these numbers,
Oh, okay.
and then that's where I got the nan. And when I changed it
Oh.
back to 1-0, it still was nan.
Oh, okay. I see. Okay. I think you have to read. Can you? Is it okay?
Yeah, yeah.
Use the computer.
Yeah,
Sorry
that's
about it.
okay.
Yeah, I think because sometimes one error is made, right, and then it's already changed to 0, 1, and then there's no yes and no yet. You run the second time, it doesn't find any yes or any
Yeah.
no, so things get messed up. So let's do
I
this.
see, I
yeah,
see.
let's do this like I can do this cell. I mean, select the cell, and then sorry, I need to. Or maybe can you do that? I don't know how to do it. Can you click on cell, and then run all the cell above, run all above. Yeah, and then you can continue to running the cell, and then okay, still nothing. So how come this? Can I show above? Like, what's the previous time you have this data set here? Yeah. So Yeah, this is okay, right? Yes and
Yeah.
no. And then can you go down? One half, yeah, and this is yes equal to one. That's a bit strange. I wonder. No show dot map. No show. Okay. Can you create maybe a cell and again just run? I mean here run before the cell and then before running this. Yeah. No, just maybe leave it blank for now. Yeah, maybe run all. No, not here. Sorry.
Oh.
Yeah, sorry. Just a cell. Yeah. Run all about. Okay. So then in this empty cell, can we try to look at the maybe examine this no-show column?
This?
Yeah. To see what does it say? Yeah, it has no's, yes and no's, right? I wonder what's different between your version and my version. No show dot map. So can you do this? And then maybe just don't do any assignment. Just to do appointments no show dot map, and then directly to see how the result will actually show up. Yeah. Yeah. Let's run it. Run this. Yeah, it looks okay, right?
Mm-hmm.
And then when you assign it back, it doesn't work anymore. I don't know why.
Because like I said, when I did this,
Yeah.
it worked.
Yeah,
and
it
then
worked.
I changed the 1 to a 2 and the 0 to a 1, and then I ran it again.
Oh, but I mean, you have rerun the whole
Yeah,
thing,
yeah,
right?
yeah.
So it doesn't matter anymore.
Yeah, okay.
I think it doesn't matter anymore because now this data set seems to be okay, right?
Mm-hmm.
And then can you maybe run the cell again? So let's try to see what happens. And then look at yeah, it's a bit strange. I mean, things were
Maybe I can delete this now.
yeah. I mean, delete this and rerun the whole thing again. No, yeah. I mean,
See.
this is okay because you already done that. I mean, yeah. Can you see? Oh yeah. So maybe because this command is supposed to be run only once.
Yeah.
Because you just ran it and then you ran it again. There's no yes and no, so
I
it could
see.
become chaos.
Okay.
So maybe go back to the cell, right, and then cell run above. Yeah, run everything above, and then you can because everything was started from scratch. Then you can do this, and then we can see. That's okay.
Perfect.
Okay.
Thank you.
You're welcome. Okay, let's start the last session of today's class. So before the break, we were talking about the prediction. Right? We predicted on the test data set, but if you get a different data set from the test data set, things can be done similarly. Right? So let's say you have a collection of new patient records. You can organize them into the format of the features as in the X part of the original data set, then you can predict on the new data set. By default, we're using the threshold 0.5, 50% to predict if a patient is going to be a no-show or not a no-show. Right? If the probability exceeds 50% by default, that's a no-show. You can use the customized threshold. So from now on, we're going to focus on the default threshold, but things can be done exactly the same way if we choose to use a different threshold level. Okay, so now we can predict based on the model. The next step is to have some idea about the accuracy or performance of your predictions. Right? We're now going to start doing some evaluations of the model performance. Two very useful commands to use. One is the confusion matrix. The other is the report of the classification, the classification report. Let's take a look at how those two methods can provide useful information for our predictions. First of all, we need to import those methods. And then this time, again, from sklearn dot metrics, right? Because we're talking about evaluating the model performance, so it's going to be metrics. And import, let's first import confusion matrix and classification. You can import two submodules in the same line, right? Just to separate them by comma. Later on, we'll also need other performance metrics, other functions from this module, metrics, but right now, let's only do those two. And then once we imported them, let's first run it. So import was complete, things are good. So let's define the confusion matrix. Let's call it CM. You can call it any other name. But CM here, we can do confusion matrix. And what we're going to do is to simply compare the prediction with the actual observations in the test data set, right? So first of all, we need the y-test. Always include y-tests first. The observations, in this example, observations of no-shows in the test data set, right? 0 and 1s. And then the second part is going to be y-pred, right? Y-pred is the prediction result we get from using the model.predict method, and that was done before the break, right? And that's going to give us the confusion matrix, and we can print it, okay? You can just do CM, but as you can see, it's going to be simply a 2x2 matrix. The interpretation of this matrix is quite simple. So let's take a look from here. I mean, we have different numbers here, but the idea is exactly the same, right? So this is a 2x2 table. For binary predictions, it's always 2x2. If you have multiple class labels, other than binary classification, we will have more rows and more columns, but it's always going to be a square matrix, okay? All right, so the row indexes of this matrix is going to be the actual observation. And the column indexes will be the prediction, right? For example, let's look at the top left corner of this table. The row index is 0, and the column index is also 0. It means that my prediction is 0. The patient will show up. In reality, the observation is also that the patient did show up, right? So this number means that among all the records in the test data set, 3, 4, 4, 1, this many patients were predicted to show up, they actually show up. Right? This is something we call true negative. Because here in this example, 0 or showing up is negative. Right? And the prediction is true, so it's called true negative. And then the second number, 1,379, right? For that number, let's look at the column index 1. It means that the columns are for predictions, right? It means that I predicted that the patient will not show up. However, in reality, the observation is 0. Those patients actually showed up, right? So for 1,379 patients, I predicted that they will not show up, but they actually showed up. Right? So those are positives according to prediction, but they are false positives. Right? So prediction was wrong. So those are false positives. They are predicted to be no-shows, but they showed up. Right? And this number, the prediction is 0. The prediction is that they will show up, but the observation is that they actually are positive. They are no-shows, right? And those are those patients who didn't show up, even though you predict that they will show up, right? Those are the false negative. The prediction label is 0, showing up, but then it's false because in reality, they didn't show up. It's no-show, right? And finally, the last cell, this number, this green number, are how many patients in the test data set who were predicted to be no-shows. They are actually also no-shows. Right? Those are the true positive. Right? They are predicted to be positive, no-show. They are indeed positive, no-show. Right? So that's a true positive. Well, as you can imagine, I want to have large numbers for top left and bottom right. Why is that? Well, because those are the true negative and true positive. Those are the correct predictions. I want to have as many predictions being correct as possible, right? And then the off-diagonal numbers, those are the false positive or the false negatives, right? Those are the wrong predictions. Ideally, I want those numbers to be as small as possible, right? So let's go back to our Jupyter notebook, right? So it looks okay, right? So the diagonal elements are somehow large compared with the off-diagonal elements. Right? So that means that maybe it's doing okay. The model is doing okay. Right? Of course, that just to tell you about the absolute number of true positive, true negative, false positive, false negative, right? So if you want to look at the total number of incorrect predictions on the test data set, it's actually 56 plus 53, right? So that tells you about the number of accurate predictions. You can easily calculate the prediction accuracy or correct rate of making predictions. But then we have another method, the classification report, which is providing more comprehensive information. So let's do this. Let's assign this variable CR, classification report. Right. Again, I need to have the y-test. Those are the observations in the test set. And we also have y-pred, right? Those are your predictions. I compare them, then I can get information on the model performance, right? It's always based on the comparison between your prediction and the actual observation. So this time, let's print CR. If you just type CR in the last line of the cell, well, it's the same thing, but the format will be less nice this time. So you can experiment on your own, but this time let's print it, okay? So it's telling us some information through this table. As we can see, there are a few things involved in this table, right? Let's look at the column names of this table. We have precision, recall, F1 score. Those are the performance metrics, right? And we actually have the performance metrics, those three metrics for both the negative records and the positive records. Let's start with the easiest thing to explain, right? So the support column is the easiest thing to explain. We see 172 here in the first row of the support column, right? It means that the corresponding row index is actually 0. It means that 172 records in the test set is 0, right? According to the actual observations in the test set, right? You examine the test set, we have 172 zeros, and then for the next number, also 172, so that's actually the label for label 1, for the label 1, right? So in the test set, we have 172 zeros, 172 ones. Right? This is not a prediction, this is the actual observation in the test set. So that's the easiest thing, I think, to explain, right? And let's take a look at the meaning of the remaining things, okay? So let's first look at the row starting with number 1, right? So let me see if I can highlight this row for better explanation. Okay, so let's first look at this row and look at the numbers as precision, recall, F1 score in this row, right? I mean, the numbers here are different from what we get from the example in the Jupyter notebook. That's okay. The idea is the same. Okay, so let's first look at precision. We have a formula for precision, and it's given here. TP is true, false, true, positive. And here, by default, positive means no show in our example. But then, because we're focusing on this row that starts with 1, it also means that 1 is no show. Okay. If later on, if you want to interpret the numbers in the row starting with 0, we have to switch the positive and negative labels, right? So for now, let's say 1 is positive, no show is positive, okay? To calculate the precision, focusing on the positive outcomes, okay, we're gonna use this formula. True positive over true positive plus false positive. What does that mean? I always find those measures to be a bit confusing. I mean, they are not that difficult to understand, but every time you have to look at the formula again. So let's look at the denominator, right? True positive plus false positive, that's everything predicted to be positive, right? To be predicted to be no-shows. And then one example, let's say I have a total number of 100 patients predicted to be no-shows, right? Either real no-shows or fake no-shows. So that's true no-shows and false no-shows. Everything predicted to be no-shows. Let's say we have 100 of them. Right? And out of those 100, let's count the true positives. Right? 63 of them, let's say, they are true positives. They are actually no-shows. So out of 100 who were predicted to be no-shows, 63 of them are really no-shows. That tells you something about the precision, or how precise is your prediction of no-shows, right? I predicted 100 to be no-shows, but not all those 100 are all no-shows. Only 63 are no-shows. Then the accuracy level is actually 63 over 100, and this is what we call precision, right? The precision is 63%. Right? So that's how we interpret the precision. It's actually precision of your prediction of no-shows, right? Look at all the no-shows, and then how many of them are really no-shows? So that's the meaning. Then we have recall, a similar formula, but the denominator is different. This time, the denominator is true positive plus false negative. Right? I mean, false negatives, they are actually positives, right? Because you predicted them to be negative, but it's false, so they are positives. Right? So in the denominator, we are having everyone who turned out to be positive. Not prediction, but actually positive. Right? Those are all the patients who were no-shows, actual no-shows. Right? True no-shows and false no-shows. Right? So it's a bit, maybe confusing, easy to mixing up, but the meaning of the denominator is that everyone who turns out to be a no-show. Right? And then for all those people, let's say I have 100 people who eventually didn't show up. And then in the numerator, I want to have the true positive. It means that I want to get an idea of how many of those no-shows are correctly predicted to be no-shows, right? So let's say out of those 100 patients who are no-shows, only 53 of them are predicted. Then this measure, which is called recall is 53%, right? So that's the meaning of recall. Why do we call it recall? Can you think of a reason for calling it recall? Well, because in order to calculate this measure, you need to know how many patients who actually didn't show up, right? I mean, when you are trying to make the prediction, you cannot get this measure because you don't know yet how many patients will show up, how many patients will not show up. It's only after everything is over, right? After the appointment day is over, I can look back to recall what actually happened. Now I recall that 100 patients didn't show up. Then I want to see how many of those 100 patients were actually predicted to be no-shows, right? So that's the meaning of recall. Recall focuses on the actual observations in the numerator as the benchmark, right? And precision focuses on the predictions. So it may be a bit confusing, but every time you want to use it, interpret it, just go back to those formulas and examples, okay? And F1 score is, it involves a certain formula. In this formula, we are basically calculating F1 score based on both precision and recall. It may look a bit intimidating, but it's very simple. All we need to know is that it's something called a harmonic mean of recall and precision, right? It's very similar just to take average of recall and precision. But in order to average up two ratios or two rates, mathematicians say that it's better to use this thing called harmonic mean instead of the arithmetic mean. Right? So that's basically all we need to know is that F1 score is to incorporate both precision and recall and get the average, right? Because they both focus on different aspects of the performance measure. So how about we come up with a score that includes both parts, right? It will somehow trade off between the two measures. All right, so then, F1 score is very useful if you are working with unbalanced data sets. I mean, here we have a balanced data set because we did oversampling. But in case sometimes you get an unbalanced data set directly fed to the classification model, and then F1 score is important, right? Because it strikes a balance between the two different aspects. Okay. All right. So then this is really the row actually starting with the number 1, right? So that's actually, sorry, let me go to the slide I wanted to show. Go back to this classification report table, right? So all our interpretations was based on this row, this highlighted row. Okay? But you have exactly the same thing, precision, recall, F1 score for the 0 row. I mean, by default, 1 is called positive, but in case you want to think about this question, what are the performance measures, precision, recall, F1 score, if I want to call 0, patient who showed up to be positive, and no shows to be negative, right? So it's exactly the same thing, only that you are calling shows instead of no shows being positive, right? So exactly the same kind of interpretation, right? And then accuracy only has actually one number, which is exactly here, right? I mean, accuracy is basically to look at the big picture. How many incorrect predictions do I have compared with the total number of predictions, right? I mean, for the test data set, I predicted for every single row in the test data set, so it's going to be that many rows as the total number of predictions, right? And then I want to see what is the correct versus incorrect predictions, right? And then accuracy tells you the rate of being correct, or the ratio of correct predictions versus all the predictions you have made, right? So that, I think that's relatively easy to understand as a performance measure, okay? And then there's a lot of descriptions here, but then let me finally explain those last two rows, right? So we have macro average and weighted average, and this is actually very simple as well. Right? So look at the first two rows, 0 and 1. Each will give you a precision, recall, F1 score. Right? And then look at the macro average score. How do I get that? Well, simple. Just the average between 0.62 and 0.63. I mean, it's supposed to be 0.6015, right? But we round it, it becomes 0.62 again. Okay? And the same thing here. This number is the average of the recall scores between the first two rows, right? And this number in the F1 score column for the macro average row, this is the average, simple average of the first two rows for the corresponding F1 score, right? So just average. And weighted average, exactly the same idea. But if you calculate the weighted average, you're going to weight those two numbers in the corresponding column by the number of instances in the support part, right? So for 0 labels, here in this example, I have slightly more 0 labels than 1 labels in a certain data set, in a certain test data set. And then when I do the average, let's say those two numbers, right? And then the 0.62, this number will carry a slightly higher weight accordingly to how many more 0 labels I have compared with 1 label instances in the test data set, right? So just to quickly summarize, refer to the formulas for those two measures, precision and recall. Precision focus on your prediction of predicting no-shows or positive outcomes. How many of them were correct? Right? Recall focus on the actual observations. Look at how many people didn't show up and how many were correctly captured. Okay? And then F1 score is going to be precision and recall taking some kind of average. And accuracy is the correct predictions versus all the predictions in the day. Right? And last two rows, macro average, just the average the first two rows. Weighted average, again, average the first two rows, but consider the number of instances with the corresponding labels as a weight. So we're doing a weighted average. Okay, so those are important, also slightly confusing, I would say. But then I guess when you apply it more and more, you will get a better and better sense of how to interpret things based on your outputs. Okay, questions? So we spent quite a bit of time on that. So if no questions, let's move on. So of course, like all those things most of the measures are included in the classification report. And there's one thing I want to mention very quickly. So let's say, again from sklearned.metrics, import, and this time let's import individual scores. I mean, those scores I will use, they are already included in the class. Oh, I don't know. So I guess somehow it started resetting everything. Sorry, give me one moment. Did I exceed time? Not yet, right? So I don't know why it's shutting itself down. So let's give it a few moments to let the projector and everything to wake up. Hopefully it will wake up. So sure. On my side, it's showing that it's still warming up. So let's give it maybe a couple of minutes to see if things will come back to life. Okay, so we have it back, which is good. So let me import the accuracy score, which is already in the classification report, right? But sometimes I want to use it separately, not involving the whole thing, right? Because maybe some analysis I want to do in the coding for using based on using accuracy score, precision score, or recall score. And there's also the F1 score, right? Lowercase. Okay, so that's to import all those individual components of score. So let me just do one quick, maybe a couple of quick demonstrations. Accuracy, let's say equal to accuracy score. It's usually always based on Y test and Y prediction, based on the comparison of observations in the test set and the predictions. Right? And then we can do accuracy. It says that the accuracy is 68%, right? So 68% of the predictions were correct. Not super impressive, but at least much better than a random guess, right? So it will have some values, depends on the difficulty of the problem. Sometimes it can be very accurate. Sometimes it is not going to be very accurate. So let's do one more thing. They are all very similar. So F1 score equal to F1 score. And then again, we're going to compare Y test and Y prediction. And finally, let's do F1, okay? Well, it's a similar number, 68.6%. Okay? I imported more than just those two scores, and you can just calculate all the remaining scores involved here in a very similar way. Okay? And later on, we're going to be making use of some of the particular scores individually instead of trying to get the whole thing at the same time. Right? Let's try to do two more things for the remaining of today's class. One thing is about the interpretation of the model, right? And I particularly want to see how the different features are different in terms of the significance of their impact on the prediction outcomes, right? And this is very similar to linear regression, right? Because the model has all the coefficients for the different features. If you have a larger coefficient, it means that this feature may possibly have a greater impact on the prediction outcomes, right? And particularly, one thing that is mathematically true is that if you have this decision function f being greater, the probability of being a positive labeled class is going to be higher, right? So if you see, let's say B2 being a large positive number, it means that it tends to increase the possibility of being positive or being a no-show compared to some other, to a greater extent compared to some other features. Okay, let's do this. So we can get the intercept and the coefficient, same thing as last time, but here, remember we have the model, right? Everything is contained in the model that has already been trained. So model dot coefficient. Let's only do the coefficient because intercept usually is less valuable in terms of interpreting the results, right? So let's just run the cell, and we can see it gives us a set of numbers, right? If you look at it carefully, we have double brackets. It means that it's actually a two-dimensional array, like a table, but here there's only one row, right? Because inside the first pair of square brackets, we only have one list of numbers. So that's a two-dimensional array with only one row. Similar to one dimension, but it's actually a two-dimensional array, right? To actually show the format a bit nicer, because we know that those are coefficients for the features, which feature is which. Right? We cannot really recall exactly here without looking at the original data frame, right? It's not very convenient. So let's do pd.dataFrame, and then this is to convert this two-dimensional array to a data frame, right? So this looks a bit nicer because it actually shows us a table, but it's still not very convenient, right? Because all those coefficients are labeled by 0, 1, 2, default labeling as the column indexes, right? So what do? I want to add back the column names, right? But the column names are the names of the features. Those are the coefficient of features. Right? Remember when we did the train test split? Actually, before we did the train test split, we have separated in the data frame into the X and Y, features and labels, right? And now those are the coefficients of the features. So we need to get the feature names, which is exactly the column names of the X part of the data set, right? X can contain all the features. It's a data frame. It contains the column names as the name of the features. So we're going to do columns equal to X dot columns. So this will actually help us specify the column names for those coefficients. Let's look at this. Okay? And this actually will give us some more useful information. Some useful information with a readable format, right? So for example, looking at those numbers, they are pretty small, which is okay because it's different from linear regression, right? It's impacting the outcome as the probability value. Probability value is small. You cannot have drastically. Not that you can't, but it tend to have small values for the coefficients for many problems. But if you quickly look at all those numbers, you will see that lead time is 0.47, seems to be much larger than the remaining coefficients, except some of the negative ones. Right? Among the positive coefficients, lead time has a good, relatively higher degree of influence on the outcome. Right? It's positive. It means that if you have a longer lead time, then probability of no-show goes up. Right? And that's intuitive because if you have a long lead time, it means that the patient is booking the appointment from a very early on time point. Right? I'm booking an appointment for a long time later, and you tend to forget it, or you didn't figure out your schedule yet when you make the appointment. So no-show is more likely. So this is the intuitive, right? And then age has a negative coefficient, not very large, but it's negative, right? I mean that maybe older people, they tend to have fewer no-show cases, right? Maybe I guess people who have retired, maybe they have more time and they are more flexible in time, things like that, right? And there are several fairly large negative coefficients like alcoholism, disability, handicap, right? Diabetes. Well, I guess that's mean that if you have a significant medical condition, you have a regular, follow-up with the doctor, with the hospital, maybe those people, because the medical issue is very significant for them, so they will make a bigger effort to attend most of the appointments, right? As opposed to the case they just want to consult the family doctor for a few minor things, maybe it doesn't make too much difference. If you go or not go, maybe you can just, find a different time later. And there's plenty of explanations. And looking at the coefficients for the day of the week, and we can determine which day may possibly have a higher no-show for patients. Okay. Anyways, that's just one way of actually showing the coefficients, right? So, and this will lead us to think about the feature importance. Let's use the remaining 10 minutes or so to talk about one, performance measure, which is also very important. And this is actually about, this is called ROC curve. And let me go back to the slides to explain, the information contained in this part, and also what is required to get this ROC curve. Right? So basically, this part we're talking about. Before we can talk about the ROC curve, we need to also talk about the two more terminologies, right? Very simple. We'll look at something called a true positive rate and false positive rate, right? And we have a formula for true positive rate. You may look at this formula, it turns out it's exactly the same thing as we call, right? So, for all the positive outcomes, observations, how many were you able to predict, right? So that's true positive rate. And there's also something called false positive rate. In the denominator, we have false positive and true negative. That's all the negative patients, right? All the patients who actually showed up. I want to see how many of them were falsely labeled as no-shows, right? That's called the false positive rate. That's not too important, but the important thing is that, there's some other alternative names for those measures. You can always go back to look at them, and there's some examples. But the important thing is to go back to think about, making predictions based on threshold, right? Remember, the logistic regression model basically provides probabilities for your predictions. Is this patient a show or no show? We get 2 probabilities, which should sum up to 1. Right? And then we also mentioned the idea of using thresholds. If the probability of being a no-show is exceeding the threshold, then I predict that that person is going to be a no-show, right? As you can imagine, if I use very different thresholds, then the prediction outcome will be different, right? Let's say you use the threshold 0.6, then a person with a no-show probability of 0.7 is going to be classified as a no-show. However, if you use the threshold 0.8, and that person will be classified as a show, right? So it's different. So the idea is that if you use different thresholds, the outcomes will be different. Then the true positive rate and false positive rate among other performance metrics, they will be different depending on the threshold level you choose, right? And then this RC curve, the full name is Receiver Operating Characteristics Curve, a term originally coming from the military. But anyways, the idea is that if you try different threshold levels, you will have different true positive rate and false positive rate, right? And then I can plot the true positive rate and false positive rates for when you're using different threshold levels, right? One example, let's say I pick the threshold level, just any random number, let's say 0.4, okay, as the threshold. Then let's say you get a true positive rate equal to this level, about 0.55, let's say. And the false positive rate as 0.2, right? And then you will add a point here, okay? And then let's say you choose a different threshold level, let's say 0.7. This time, let's say you get a false positive rate of 0.4, and the true positive rate is about 0.7. Right? I add a different point here. Right? I will do this for many, many different threshold levels. Eventually, I connect all those points to form a curve. And this is called ROC curve. Okay? And then, if I get this ROC curve, this gives me some idea about the false positive rate and true positive rate when you manipulate the model with respect to threshold levels. Now, question: if you see a red curve as the ROC curve like this, how do you say if the prediction outcome is good or the performance is good? Right? It's difficult to tell maybe from here, but let's do another thing. So let's say you use a different model, right? So those things are not necessarily only for logistic regression model. It can be anything. Okay. Let's say you use a different model, and then let me use a different color. Pen color, blue. Let's say you use a different model, and then you get a different ROC curve like this one. So the red curve or the blue curve, which one actually suggests a better performance of the model? What do you think? How do you tell? Use different models, right? For each model, you manipulate the threshold level. Then you can plot the relationship between false and true positive rates. You get two different curves for the two models. If they look like this, which one's better? Any thoughts? Any guess or thoughts? Well, you think about this way, right? I want to have a low false positive rate. I want to have a high true positive rate, right? It means that I want to move to the left. I also want to move to the top, right? Then you compare the two curves. if you're moving from this red curve to the blue curve, for every point you're moving toward the top and toward the left, right? That's why the blue curve is better, because it gives you a lower false positive rate but a higher true positive rate. Right? So that's why blue curve is better. Now we can actually use a particular number to, to quantify this comparison. How do we do this? Well, there's some term called AOC, area under curve. Right? For the red curve, I calculate the area under the red curve. For the blue curve, again, I calculate the area under the blue curve. We'll see that the area under the blue curve is greater, right? So a larger value of area under the curve will be suggesting a better performance. So that's how everything started from this for this ROC curve and how they suggest your performance. The last couple of minutes, let's see if we quickly do some implementations in Jupyter Notebook. Okay. So this time we're going to implement the ROC curve. We're going to plot it, also calculate the area under the curve. Right? So let's do sklearn.metrics. And then I want to import two things. ROC curve, that's helpful for me to plot the curve. And the other thing is ROC AUC score. That's the AUC score, right? And then let's also import matplotlib.pyplot as PLT. Okay. So then I'm going to use the function. This function is called ROC curve. And then, as usual, the first argument is test, because I want to compare test with prediction, right? But for the prediction part, this time I'm going to use the probabilistic prediction and focus on the second column, or the column with index 1. Right? That's the probability of being no-shows, probability being positive, right? And then there will be 3 outputs from this function if you do this comparison. The first output is going to be a list numbers, FPR, false positive rate. And then I will get the true positive rate, TPR, and then I will get the thresholds. I mean, what it does is that it will automatically select a list of thresholds. For each of the thresholds, it calculates the false positive rate and true positive rate, all right? So, and then as the output, it tells you the threshold it has experimented on, and also the corresponding false and true positive rates, okay? And then once I get this, it's very simple. I'm going to plot a line graph, FPR, TPR. Right? So nothing but just to plot the false positive rate against the true positive rate. And then let's show it. Okay, so this is the ROC curve. A bit noisy, right? Because it's not smooth, because the real data are kind of very noisy. I mean, you can add X label, Y labels to save some time. Let me skip it for now. And then the one last thing to calculate the area under the curve score. And it's actually very simple. Let me just quickly demonstrate how we can do it. Okay, it's very simple. So remember, we imported 2 measures, 2 functions. The second function is ROC AUC. AUC is area under curve score. And then we're going to provide y-test, and that's the actual observations, compared with the probabilistic prediction, and focus only on the second column, which is the probability of being positive. Okay? I mean, because when you are manipulating with the threshold levels, you need to compare the threshold level with the probability of being positive to get the actual predictions, right? So that's why we need this one. And you use different thresholds, depends on, based on this probability numbers, you will get different positive and true and false positive rates, right? And then we can just do AUC equal to this number, right? And AUC, so it's actually 0.72. Okay? Well, it's difficult to tell actually if this is a good performance or bad performance. But it really depends on the context, right? So for some very difficult problems, even a very low score may be good enough, right? But in general, there's some rule of thumb. If you have a score of 0.5, then it's the same as a random guess, right? Because the false positive rate and the true and false positive rates will be equal to each other. So it's the same as a random guess. So it's useless. Right? If you get a score of 0.7 or higher, generally it's considered to be acceptable. It may not be super good, but at least acceptable. If you get 90% or higher, then it's fairly good usually. Okay, so that's just some rule of thumb. I mean, the way you interpret it, it's really depends on the problem. Okay, you're making, classifications about the financial market. It's very difficult. Otherwise, everyone's going to be rich. Then even the low score, slightly above 0.5, is acceptable. Okay. All right. So for today, let's stop here. We didn't actually finish the whole Jupyter notebook. So next time we are going to pick up from here to talk about how to select features for a prediction model. Right? So thank you very much for coming today. So I wish you will enjoy the rest of the week.